Hello, this is the first tutorial for beginning to work with ANSYS for EGA324. The first example we're going to look at is a very simple one-dimensional cantilever beam with an end load fixed at the other end. This is a very basic example of Euler-Bernoulli beam theory. For more information on solving the theoretical solution, you should revise your stress analysis notes from previous years, or if you follow the link on the screen, the original version of this tutorial also goes into some detail on the theory behind it. In this video, we're simply just going to look at using ANSYS to solve the deflection and the bending stresses in the beam with an end load. So the first thing you're going to want to do is to open ANSYS. If you're doing that on the Engineering PC Labs, go to the Swansea Unified Desktop icon, click on Specialist Apps, College of Engineering, ANSYS, and you should find ANSYS Workbench in that folder. When you open that, you'll be presented with a screen which looks like the one in front of you right now. We'll refer to this as the main ANSYS home screen or the project schematic screen. So the first thing to notice, on the left hand side in the toolbox here, you've got a number of different analysis systems which we can add into our project. This example, it's a static structural problem, so double click on static structural and it will add that analysis system into your project window here. Let's just rename it something like example 1 cantilever beam. Okay, so the first thing we need to do is to tell ANSYS what material data we're working with. Now you can see the first step here in the system, engineering data, already has a tick next to it. That means that this is already set up, ready to go. By default, ANSYS has added structural steel as the default material, but of course we can change that if we want to. So double click on engineering data, and that will open this new tab. You see this tab is opened at the top of the screen here, A2 engineering data. From here we can see what material we already have assigned to our modeling system, and we can choose more if we want to. So notice these two buttons just underneath the tab here, filter engineering data. That tells us what material we already have in our project. In this case it's just structural steel, and the lower window here gives me all the material properties of that steel that I'm working with. You can resize the windows by dragging in and out like this, or you can go to View, Reset Workspace, and that will bunch the windows up in a neat way. To add a different material, go along to Engineering Data Sources, and this gives you some general categories of materials to choose from in the top window. So let's just have a look at general materials. In the middle window here, it will give me all the materials that ANSYS has in its library under general materials. So I can choose one from there, and in the lower window it'll give me all the material properties of that material. In this example, we are only working with structural steel, so simply deselect engineering data sources, make sure under filter engineering data you have structural steel included in the project, and then we can close the engineering data tab. Okay, so step 2 is to define the geometry that we're going to work with. So double click on geometry and it will open a new window. It's still part of ANSYS, but this is called Design Modeler. It's where we input all the graphical data that represent the model we're working with. So for the cantilever beam example we're going to solve here, we're going to do it in the most simple way possible, and that is just to draw the beam as a one-dimensional line. We're not going to draw the beam as a 3D shape with a 2D sketch and an extrude like you might do in SolidWorks. We could do it that way, but the number of mesh elements that will create will result in a very long computational time, and it's a very simple example. So notice the windows we have. We have the graphics window here, we have the tree or project outline here on the left hand side, and we have a details window underneath. Currently we don't have anything drawn, so there's not really any details to see so far. The next thing to notice is you have two tabs here, sketching and modeling. So if you go across to the sketching tab, this contains all your drawing commands. Before we do anything, the first thing to do is go up to units and check that we are using millimeters. By default it's set to meters. I would suggest using millimeters because in mechanical engineering most of the time we're going to be working with millimeters. In this case we're going to draw a 4-meter beam, but I would suggest it's good practice to always make sure you're working with millimeters. So next thing to be aware of, the little XYZ axis controller in the bottom right corner here. This will help you zoom and pan around the geometry that you draw in. You can simply hold down the scroll wheel or the middle mouse button and drag this around into, well, to get a 3-dimensional view, or you can use the controllers here. So if I want to look in isometric orientation, click on the light blue dot. If I want to look at the XY plane, I can click on the Z axis and it will automatically zoom into 2 dimensions there. So come along to the sketching tab, click on settings, click on grid and turn on show in 2D and snap. Okay, so that shows the grid on the XY plane and it snaps anything I draw to the grid lines. Okay, go up to draw and select line. My mouse has turned into the pencil symbol. That shows me that I'm in draw mode, and if I hover near the origin, I click once to start drawing a line, drag it out some distance along the x-axis and click once to finish. I'm going to press escape on the keyboard. Okay, and I'm finished in drawing mode, and that's really all I need to do in order to get the geometry drawn. I do need to give this a dimension though, so to make sure it's the correct dimensions. So come across to the sketching tab again, click on dimensions. General is already selected, so click once on the line, drag the dimension some distance away, and I'm dragging it quite far away because when I change this to 4000 millimeters it'll disappear right off the edge of the screen, so I want the dimension to be quite far away. Okay, and now here you can see in the details window it's given me all the details of that dimension I've just drawn. It's telling me that the length is 132 millimeters, so click once, overwrite that with 4000. As you can see it's disappeared way off the screen, so come up to the top, find the zoom to fit icon and click it, and that'll show you your 4-meter line on the screen. Okay, the grid has disappeared because I'm zoomed so far out, it wouldn't be able to show the grid at that resolution. Next thing I need to do is to actually turn that line or that sketch I've drawn into a body that ANSYS can analyze. So come up to the top of the screen, click on Concept and click on Lines from Sketches. And that's going to turn this sketch into a line body. It's automatically switched back to the modeling tab here. Okay, I can't switch back to sketching until I've done the next operation. So look in the details view here, it's asking me which object do I want to apply this body to. So it's going to be this line that I've drawn here. That's what I want to turn into a body. So I click once on the line to select it and I click apply. Okay, and now base object has been associated with that piece of geometry. It's still not quite finished, even though the line body has appeared in the tree outline here. It's got a yellow lightning bolt next to it, which means it needs to be generated before we're ready. You can either click generate at the top here or right click and generate, and there we go, it's got a green tick next to it, and that means that that sketch has now been turned into a line body and it's appeared in the tree outline here. Before we're finished with the geometry, we need to tell ANSYS what the cross-section of our beam is. Okay, so if we click on line body, we can see that currently in the details view it says it doesn't have a cross-section associated with it, and we haven't drawn the cross-section, so we can't associate that next. So in order to draw in the cross-section, come up to Concept, Cross-section, Rectangular. Okay, now this opens what is effectively a new sketch. Okay, don't worry about the fact that we appear to be sketching on the same plane. Okay, it doesn't matter in this case. We're not sketching on the same drawing as our line. This is effectively a new sketch. It doesn't matter what the orientation is. All that matters is that we have the correct cross-section, and currently in the details view we have a 10 by 10 millimeter cross-section. The actual problem specifies that the beam is 300 by 300 millimeters. So I'm just overwriting the value there. Again, it's disappeared off the screen, so use zoom to fit. And there's our square cross-section. Okay, and you can see that that cross-section has also appeared in the tree outline. It's got a green tick next to it. The final thing we need to do before the geometry is complete is to associate that cross-section with the beam. So click on line body. Now where it says in the details window there's no cross-section selected, all I have to do is click on the arrow and select that cross-section that I've just drawn. So rect1 is the name of the cross-section that's appeared here. So select rectangle 1, and there we go, everything's got a green tick, so that cross-section has now been associated with the line, and we have a beam 4000 millimeters in length with a cross-section of 300 by 300. We can see that in what is effectively 3 dimensions if we go to View and select Cross-Section Solids. Let's look at it in isometric view. There we go. So we can see, even though effectively all we are modeling is a single line, we have what looks like a 3-dimensional beam. Okay, so before we move on, let's File, Save Project, give it a suitable name. Save this to your own student number folder directory on the PC Labs. It doesn't have to be the same name as your analysis system, it just makes sense to me. Okay, so geometry's got a green tick next to it now. That tells me that we're ready to move on to the next step, which is to define the mesh. Double click on model, and again this will open up another new window. It's still part of ANSYS, but this is ANSYS Mechanical Solver. Okay, as you can see, it's a new window. It's not part of the project schematic window, but this is the window we're going to use to solve the rest of the problem from now on. You can see it's imported our geometry across. We have the line here on the screen. It is just a line at the moment, and because I am looking at the geometry that we've imported, again, if I go to View, Cross-Section Solids, I can toggle between the line view and the 3-dimensional view. Now what I need to do is to create a mesh, and you can see there is a mesh option in the project outline here. It's got a yellow lightning bolt symbol next to it, which means there is something there, but it's not yet been generated. So let's generate the default mesh and see what it looks like. Right click, go to Generate Mesh. Okay, it automatically gives me the 3-dimensional view when I do that. So this is just, ANSYS has decided on a default mesh for this beam. If I look at the statistics, it's decided to give me 21 elements. But obviously we'd like a little bit more control over this. 21 elements for something this simple isn't really necessary. So what we want to do is add a mesh control, or a mesh sizing option rather, to our mesh. So select mesh here, and you'll see in the toolbar above the outline you get a new menu of options associated with meshes. Mesh control, click on sizing, and it adds a mesh sizing option to our mesh in the outline here. First of all, it's asking me what geometry do I want to associate this mesh sizing control with. Obviously that's our line here. So if I click where it says no selection, what I want to do is select our line. At the moment you can see it's not letting me select it. It should turn dashed red. The reason it's not letting me select anything is because of these options in the toolbar up here. at the moment, the option I've got selected will only allow me to choose a surface, but we don't have any surfaces, we only have a line. So you need to click on the button that allows you to select lines. Now I can select the line body, click on it once, click apply, and now our sizing control is associated with the line. Again, look in the details window, and we want to define, well, we could choose the element size, divide the length of our beam into a known dimension, or we can just choose number of divisions down the entire length of the line, and let's say we want 10 evenly spaced divisions. There we go. We've now changed the mesh sizing so that there are 10 evenly spaced divisions. We need to regenerate that mesh, so right click, generate mesh, and now instead of 21 elements I have 10 elements down my beam. Okay, and now I'm working with the mesh rather than the geometry. If I come up to view, the option to toggle between the three-dimensional and the line view is now thick shells and beams. I know that's a bit confusing, but when we're just working with the geometry option, it's cross-section solids. When we're working with mesh, it's thick shells and beams. So if I turn that off, I can go back to my one-dimensional line and nodes view. So this is what the mesh looks like in one-dimensional view. Okay, so let's leave that option turned off for now. Let's look at the one-dimensional line, because I want to apply a fixed support at this node right at the fixed end, and I want to apply a load at the free end here. So come down to where it says static structural, and again you'll get a new set of options in this toolbar just above the outline. First thing we want to define is the fixed support, so click on supports and fixed support. Again, it's asking me which geometry do I want to apply the fixed support to. So what I want to choose is this point right at the end. At the moment it's only going to let me select the line. That's because I have the line selection option. I want to change it to the point selection. And now I can choose this point at the fixed end. Click on it once, it'll go green. Click apply, and now we have a fixed support at that end of the beam. Obviously a similar method to apply the load. Click on loads, force, and again it's asking me which geometry to apply it to, so I want the free end. Apply. Now to define the force, instead of defining by a vector, I want to define by components, and the y component will be a force of 8,000 newtons, but in the negative direction. And the red arrow appears to show me in which direction the force is acting. Okay, so that is the setup of the problem almost complete. The next thing to do is to solve, but before we solve, in fact we can solve and see what happens. The progress bar will appear down the bottom to show you how far through solving ANSYS is. Okay, so everything's been solved. We've got a green tick, but we don't actually have any results on the screen because we didn't tell ANSYS what results we actually want to look at. ANSYS doesn't know exactly what results we want to see. We want to look at the deflection and the stresses, so we need to tell ANSYS which results to show us. So with solution selected, again you will see you have a new set of options in this toolbar. Click on deformation, click on total, and it will add the total deformation results to the solution. Again, it's got a yellow lightning bolt, so we need to right click and resolve or evaluate all results, and now that will solve the deflection for us. In 3 dimensions it's not immediately obvious what's going on, so let's look in 2 dimensions. So here we have our fixed end, and at the free end, due to the 8,000 Newton load, we have a deflection of 1.27 millimeters. Let's have a look at the thick shells and beams option, and that gives us something that looks a little bit more recognizable as a beam. And currently we have just the deformed shape with the mesh elements visible. If you click on the result, look at the options again in the toolbar up here, you can select Show Undeformed Wireframe to see the original outline of the beam before the deflection. The result is obviously exaggerated. This is not representative of 1.3 millimeters of deflection over a 4,000 millimeter beam. The scale is actually exaggerated. If you want to look at the true scale, you'll notice the actual deflection is pretty much negligible. But in order to get an idea of what's going on, the auto scale is often greatly exaggerated, so just be aware of that. Let's have a look at some of the stress results. So come back to solution, and you'll notice if you try and add a strain or a stress or an energy result, all of these options are now grayed out. We can't actually add them. This is simply because of the type of problem we are solving here. It's a very basic one-dimensional problem, and so the normal stress strain options don't work here. What we need to do is come along to Tools under the Solution toolbar and add a Beam tool. And that will add the beam tool into your solution. If you expand that out, you'll see it already has some stress results assigned to it, but we can add some more. Up the top here under beam tool options, let's add the maximum bending stress and the minimum bending stress. Right click and evaluate all results. Okay, and so all our stress results have been analysed. As you can see, the results give me a numerical value, so 7.11 megapascals of stress at the fixed end, and what is a very small number times 10 to the minus 15, which is effectively zero stress at the free end, which is what we would expect. Let's have a look at the minimum bending stress. Okay, so again, don't be too confused by the scale. Because these are all negative values, the red value is actually what appears to be effectively zero stress again at the free end, and we have a negative stress again at the fixed end, which is equal and opposite to our maximum bending stress. Let's have a little think about how we interpret this, because although that is our ANSYS solution finished, we have our stress values and our deformation values. Because we have only analysed this as a one-dimensional beam, it's not quite giving us an accurate representation of the stress distribution over the fixed end. So what is actually happening? Yes, we would expect the stress to be maximum where the beam is fixed to the wall, but in terms of understanding the maximum and minimum bending stress, we have to think about what's going on over the 300 by 300 cross section where the beam is fixed. In actual fact, what will happen if I turn on thick shells and beams? In actual fact, what will happen is that our maximum bending stress will occur at this top corner here, where the stress is in the tensile direction, the beam is being pulled away from the wall, and that gives you a positive bending stress of 7.1 megapascals. At the bottom of the beam, the stress is in the opposite direction, so the stress is a compressive stress pushing the beam against the wall, and that's why it's a negative 7.1 megapascals. In the middle of the beam, the stress will be zero, so you have a positive 7.1 megapascals of tensile stress at the top, and then a slow, even distribution of stress to a negative 7.1 megapascals, a compressive stress at the bottom. The reason ANSYS doesn't show this is because what we have actually solved is this solution, just a one-dimensional beam, and you can't distribute stress over a single point. So when we look at that in 3D, it's slightly misleading. It's not entirely accurate, but at least it gives us our maximum value, which does correspond with the theory. Okay, so if we'd solved this in 3 dimensions, obviously we would have been able to see that stress distribution. But for the purposes of this very basic example, this result is good enough as long as we understand the theory behind stress distributions. Okay, so make sure now you file, save project. You can close the mechanical solver window, and you don't need to save again. If you save in one of the other windows, it will save the project automatically, but let's just make sure we have this saved. We will be returning to this in example 3, so make sure you keep this example 1 set up because we will be using it again later.